All right, how's everybody doing?
Good, are you?
Doing well, thank you. So questions. I have not graded homework 4 yet. That will happen probably this weekend. Um, well, we can still talk about questions on that. We can talk about questions on the lab, and we will start talking about state machine synthesis after that, which will be homework 5.
So for Lab 5, I sent you an email about it. I can't get my circuit to reset back to 0.
Right.
I put it through like an AND gate and then set it to the 2 reset inputs on, I can't remember what the chip is, I think it's the 93.
Mm-hmm.
But it sets it to 8 after it gets to 9 and then it stays there.
Okay, so what did you put into your AND gate first of all?
So I did, let me try and think, it's like 1 0 1 0.
Okay, so 10, right?
Right.
So you ANDed all 4 of those together?
Just the 2 ones, not the other 2 zeros.
Okay, so we have this circuit, it's counting, right? And there's some kind of clock input. And every time the clock ticks, this should count. Okay, let me just call these bit 0, 1, 2, and 3. They're actually called QA, QB, QC, QD, but let me talk more generally than that. So this is going to count in the usual way. And what we'd like to do is when it gets up to 1001, which is 9, we'd like the next count to be 0, right? So that it goes back. So first of all, how do we force this counter to go back to 0? It has these reset inputs, R01 and R02. And go back to our truth table. If R01 and R02 are both high, then the count will go to all zeros. Okay. So, and we have to make sure whether that's a synchronous count or an asynchronous count. In other words, as soon as you set those inputs low, does it immediately go to 0, or does it go to 0 on the next clock tick, right? And I'm thinking from this, it's going to go to 0 immediately, but let's see. It doesn't actually tell us. So let's play with this. Let's just wire up one of these and see what happens. So I'll put a breadboard in here. I'll get a 7493. And I'm just going to get some LEDs. And some resistors. And yeah, basically we want to make a circuit that'll cause it to reset on 9. And do we want to reset on 9 or 10? I'm not sure. But you know, if we were in the lab, we would start pulling parts out of the box and putting them into a board and seeing what happens. And that's basically what I'm going to do here, is just kind of see what we can get. How do I make a clock signal for experiment 1? So let's play with the 555 right after this and see how to get a clock out. Okay. Alright, so that's our power supply. And let me run my standard wires here to connect up VCC and ground. And I don't actually remember which way these things go, so I'm going to just do a test and turn this on, and that does not seem to work. So let me do this. Alright, run that our LED's on. So the straight wire is ground and the one that's bent goes to power. So let me pop down a bunch of resistors here. Connecting to ground. And we'll run some wires. Alright, so I can take the outputs of my counter and connect them to these pins and use that to light up my LEDs to see how it counts. Okay, so let's explore that. I already have this. Alright, so there's a 7493. Power on 5, ground on 10. So 1, 2, 3, 4, 5 goes to power. We'll color code it. 8, 9, 10 goes to ground. We'll color code that. And it's nice to keep your wires kind of as short as possible. Right, if you're doing this on an actual physical board, you wouldn't want a bunch of wires in the middle here. So let's hook up our output. So our output is pins 12, 11, 9, and 8. So 12, 11, 9, and 8. Alright, so this should be least significant bit, most significant bit. And to start, we're going to take pins 2 and 3, and we're going to drag those low. Okay, we're going to connect them to ground, and then we'll figure out how to make this thing reset. So we want both of these to be low. That's 12 and 13. Or, sorry, 2 and 3. So connect those together, and we'll pull that to ground. And then remember the trick that I told you? The one thing you need to know to definitely make this work is connect pin 12 to pin 1 and then use 14 as your clock input. So let's connect 12 to 1. And then 14 is going to be our clock input. So I'm going to, I'll just use a dip switch. And let's just use this rightmost part of the dip switch. And let's wire that up. So we'll put a resistor to 5 volts. We'll connect this side to ground. And we'll take pin 14 from that point. So flipping this switch should do the same thing as having our clock toggle. Okay, so let's see what this does. Right now the switch is off, so I've got a logic 1 going into my clock. Okay, this sets it to a 0. This sets it to a 1. Well, that was unexciting, wasn't it? So it is doing nothing. Alright. So let's double check what we did. This is the clock input on 14. 13 has no connection. 10 should be ground. That's 10. 5 should be power. That's power. The switch isn't touching the other side. That is in fact a problem. Thank you. That would have been like the last thing I checked after an hour of checking wires. Alright, so let's run this. So the switch goes low and my output is reading 1. Switch goes high, switch goes low, the output jumps to 4, so I miswired something. And then it goes to 5, and then it goes to 8, and then it goes to 9, and then it goes to 12. Alright, so I miswired something in here, but it's counting. Okay. And it may be miswired, or it may be that you know, it's a really good simulation, because if you actually build this circuit in the lab and you flip this switch, this is what you'll see. You'll see strange behaviors. Okay. So so let's talk about that, and then we'll go back and we'll wire up the counter for experiment 1 and see how this works, and then we'll talk about how to roll over at 10. But let's think about a switch for a moment. This is our picture of an ideal switch, right? And you flip the switch down and it's closed, and now you have contact, and you flip the switch open and you don't have contact anymore. But mechanically, right, this is what? It's one piece of metal moving through space to make contact with another point of metal. So if this is a push button, you may have something like this, right? And then up here you would have, you know, a piece of metal connected to a push button, and some kind of spring that's making it hard for this thing to make contact. When you push on the button, this moves down, and eventually this piece of metal makes contact with this piece of metal. And this is one of your wires, and this is another wire. So pushing the button connects this end to that end. But think about what's happening when you have a mechanical universe, right? As you apply pressure on this push button, the spring compresses, this piece of metal comes down, and eventually it touches this plate. Well, when it touches that plate, what's going to happen? It's going to bounce back a little bit. And if you put on just enough pressure to just barely make contact, the bounce from that, coupled with the spring, is going to cause it to lift up a little bit, and it's going to break the contact. Now, if you keep applying force downward, it will come back and it will make contact again. And maybe this piece of metal here will deform a little bit, and it will break contact momentarily until you push it down even further and it makes contact again. So when we close a switch like this, we picture, you know, 0 volts, 5 volts. But the reality is you actually get something like this. Okay, you get these glitches, and this is called switch bounce. And if you were to build this circuit in the lab and flip the dip switch, you would actually see that it registers more than one pulse. Could be 2 or 3 or even more. Okay, so I think that's what we're seeing here. But let's go ahead and build a circuit from experiment 1, which will generate pulses without any of these noisy glitches. Okay, and let's see what we get from that. So I'm going to keep this here. I'm just going to pop another proto board in, and let's wire the circuit from experiment 1. Let me put it over here. Okay, so there's a new breadboard. Let's connect our power and ground. And let's take a look at the lab. So we're using a 555. We're told to wire it up like this. Okay, so let me bring this into focus, and let me shrink this down. Done with that. Alright, and let me use this as my wiring guide. Alright, so we need a 555 chip. Let's grab one of those. I'll put it right in the middle here. Alright, so how do we connect this? Pin 1 goes to ground. Okay. I'm going to color code that. Pin 1 goes through a capacitor to pin 2. Okay, so I need a capacitor. I'm going to put my capacitor right here. I'm going to connect pin 1 to one end of the capacitor. Pin 1 to one end, and the other end goes to pin 2. Okay, so that's this piece of the wiring right here. And the capacitor, it says up here we should set it to 1 microfarad. Okay, so I'm going to come in here, I'm going to select microfarads, and I'm going to set this to 1. Alright, pin 2 also connects to pin 6. So let's take a wire out from pin 2. And let's bring this over to pin 6. Okay, so now I've got pin 2 connected to pin 6. Pin 2 also goes through a resistor to pin 7. And that resistor is going to be 1 mega ohm. Okay, so pin 2 goes through a resistor to pin 7. So let's pop a resistor in here. Let's make this 1 mega ohm. And let's go from pin 2 to one end of the resistor and the other end of the resistor to pin 7. Okay, so that's this wire right here. And then pin 7 goes through a resistor to pin 8. So let's pop one more resistor in here. And let's rotate this. Okay, so resistor goes between pin 7 and pin 8. So let's take pin 8. Let me move this. Yeah. Let's take pin 8 and connect it there. And let's take pin 7 and connect that to the other end. Yeah, rotating is kind of cool. It doesn't work well for switches. They don't actually rotate the way you'd think. But for resistors, it's handy. And probably for LEDs too. So yeah, rotating again, I just use this symbol up here. Once you select a part, that'll rotate it. Alright, so we've got the resistor from 7 to 8. That's also supposed to be 1 mega ohm. What else do we have? Pin 4 should go to pin 8. Well, pin 8 is going to go to power. So let's put that connection in, and we'll color code that. And then pin 4 also goes to VCC, which is power. So I'm just going to draw a wire from here to pin 4, and I'll mark that red. And then pin 3 is our actual output. So let me put a wire over here. That's our output. Let me color code that turquoise. And then pin 3 goes through a 1K resistor to pin 8, which is VCC. So let me pop a resistor in here between VCC and my output from pin 3. And I think we've got everything except for this 0.01 microfarad capacitor. So let's just take one more capacitor, and it's really connected between power and ground. So I can pop this in here, and let's rotate that part. Yeah, it's not going to let me do that. So let me put this, let me just put this over here. And we'll make this 0.01 microfarads. And we'll connect one end to ground and one end to power. Alright, I think we've got everything wired up here. So VCC to 8 through a resistor to the output, through a wire to pin 4, through a resistor to pin 7, and then 7 to 2. 2 is connected to 6 through that big long wire. 2 goes through a capacitor to 1. We should be all set. So let's put an LED on the output and see if it does stuff. So I'm going to put an LED right here, and let's see if we can rotate LEDs. That's kind of weird looking, but I guess it's okay. Okay, so we said the straight leg goes to ground, right? So let's put a 1K resistor between the straight piece and ground. And there's our LED. Let's see what this does. So we will turn it on, and my LED is blinking. Right, so it's on for about 1.5 seconds, and it's off for about 1/2 second. Okay, that's the behavior you want out of this device. Okay, with those values of the capacitor and the 2 resistors, microfarad, and each of those a mega ohm, this should blink at about this speed. And if your LED isn't blinking, then there's probably a wiring issue somewhere. And try to catch me in office hours, and we can look at it. Although I'll confess, my office hours are getting totally booked right now, so it's kind of hit and miss whether you'll be able to catch me there or not. But the 8 o'clock office hours are mostly open. The 11 o'clock ones are pretty much non-stop students. But double check the wiring, okay? One thing you can do is you can take a multimeter and you can measure your voltage at different spots, but just really carefully check the wiring and make sure that it follows this diagram. One thing that can help is color coding. So if you have like colored pencils or markers, you can color this wire blue and then make this wire between 2 and 6 the same color, and that can help with finding wiring errors. Power and ground, always good to do red and black, or some pair of colors like that. Alright, so if we get this blinking, then we should be able to take this, and instead of coming from the switch, right, so we were reading from pin 14 was our main input. Instead of coming from the switch, let's come from from over here. Oh, we'll just go from pin 3. Okay, which is going to the LED. So let's run this. So there's 1. I still have a wiring problem. And then this one's going to go on. Alright, so it's counting, but it's counting in a goofy way, right? So let me double check my wires on this 74 HC93, which I closed the window for. I shouldn't have done that. But I thought we were done. So our output should be pins 12, 9, 8, and 11. So I'm going to write those down. 12, 9, 8, and 11. Yeah, I think it's just the 2 middle ones are swapped. So 12, this wire should go to the first bit. And the next bit should come from pin 9, which is going to the wrong spot. So pin 9, this should go to the second bit. And then the third bit should come from pin 8, which is right here. And then the fourth bit should come from pin 11, which is right here. So let's see how that does. So there's 1, 2, 3, and 4, 5, 7, and there's 8, and that's 9 and 10. So now it's counting correctly, right? It's going up through 15. Why not color code your wires connecting to the LEDs to find out what is causing the problem? Yeah, that would be a good idea. That would help a lot. And somebody else says, my circuits always look like a rainbow when I'm done. That's cool. Izad's circuits always come out really beautiful on this. He does nice color coding, and all his wires are straight and have nice 90-degree angles. And mine are kind of sloppy. I'm a software person, right? I'm a computer science person, so my proto boards don't look as nice as Izad's. But Tinkercad, it's fun to try to lay these things out and make them look nice, make the angles nice, and so on. You used to be able to actually go to Radio Shack and buy little plastic trays of wires that were pre-cut and pre-bent, and you could use these to make beautiful circuit boards, right, that came out looking really nice and easy to follow. Right, and a lot of times this is what your circuit boards end up looking like, right? And I've known people who actually built boards like this and could actually tell you what was going on and could like debug these circuits effectively. But yeah, so Tinkercad is a little easier to do that. All right, so and you can buy a lot of wires from Amazon, and they come color coded, and you can sometimes get them in different lengths. But most of the wires you get there are flexible, which is nice because they don't break as easily. And you know, if you're making something really showpiece, you can actually like glue these wires down with a little bit of glue to hold the shape. But then you're kind of defeating the idea of a proto board, which is rapid prototyping. But you know, you can do all kinds of stuff with this, and proto boards are actually called breadboards because people used to actually use old breadboards made out of wood, and they would put nails into them and use the nails to make connection points and wrap wires around them and so on. So these are all good things. All right, so this brings us to the original question, which is sort of the last part of this, which is how do we get this counter to reset so that when it gets to 9, it goes back to 0? So I've got a switch sitting over here. I'm going to try something. These 2 pins, 2 and 3, that I have connected to ground, instead of connecting those to ground, I'm going to connect them to a switch. So I'm just going to connect them right here. And with my switch on, those should be both connected to ground, so this should still be counting as usual. Okay, so there's my 1 and my 2 and my 3 and so on. So the question is, what happens when I flip the switch? Will it count back to 0 immediately? And it does. And it stays at 0. So there's a 2. As soon as I flip that switch, it goes back to 0. All right, so we touched on this briefly last time. This is what we would call an asynchronous clear. It's asynchronous because it does not matter where the clock is. The clock could be high, could be low, could be changing, could be not changing. As soon as these clear inputs go high, the count immediately goes to 0. Okay, and that might actually be in here somewhere. Nope, they don't actually mention that. So what can we do? Well, the idea is, if we go back to our original count, which I don't have anymore, when we get to 1010, we want this to go back to 0, right? So this clear input should be asserted exactly in one case, which is where your output values are 1010. Alright, so there's your counter, there's the outputs, here's the bits, this is least significant bit, most significant bit. Right? And when you get to the case where your outputs are 1010, that's when we want this clear input to become a 1, which means as soon as it gets to 10, it will reset immediately back to a 0. So it'll count 0 through 9, it will briefly go to 10 for like a fraction of a second, and then it'll jump back to 0. So if you hook this up to your 7-segment display, you should see a pretty steady 0 through 9, and then after 9 you should go back to 0. So how do we make this clear do this? Well, write a sum of products. So QD ended with QC bar, ended with QB, ended with QA bar. So take all 4 of these outputs, invert 2 of them, and all 4 of those together, feed that into your clear, and you should have what's called a modulo 10 counter. Counts from 0 to 9 and then back to 0. Does that make sense? So I won't build that here, but get yourself a 4-bit AND gate or a couple of 3 input AND gates and put them together. Because I don't think you have a 4 input AND. Oh, you do. You have a 4 input AND. So you'll need that. You'll need a 7404 to invert 2 of your output bits. So make another Proto board, right? Feed those in, and then use that to drive the clear input. And you should get a good mod 10 counter.
Nick, I have a question about the system diagram.
Okay.
So for the inputs, should we include stuff like the timer and the clear and all that?
So the system diagram for this lab is a little strange, right? Because really, at some level, there's no inputs, right? And the final output is a display. But what you could do is you could do something more like a block diagram, right? Have a timer, and that sends an output into a counter, right? So this is your clock, this is your output, and your counter has 4 outputs, which we'd call, you know, A, B, C, D, and those go into a decoder, and that generates 7 outputs, which are A, B, C, D, E, F, G. Right. So that's a more detailed system diagram than just a single box, right? But it's really the 3 pieces that you're building. You're building a timer circuit, right? Experiment 1. You're connecting that to a counter, experiment 2, and you're feeding that into a decoder and 7-segment display from lab 4. So something like this would be fine. I'm not gonna grade people harshly for the system diagram for this one, because technically, you know, this is kind of what your system diagram really looks like. You don't actually connect any inputs to this or connect the outputs to anything. It's a self-contained unit, right? But to make your system diagram more interesting than this, I would say, yeah, just do, you know, the system diagram for the 3 main pieces and connect those together like this, and that'll be fine.
Okay. And for the schematic, should we include the design for the timer?
Yeah, the schematic should be everything. So it should be the timer, which is going to be, you know, this thing, with the output connected to the 7493. Now for the 7493, again, we don't have a standard logic symbol for that. So you can do something like, you know, just draw a box and label it U5, and U5 is a 7493. And if you want to connect to pin 14, right, just connect to pin 14. It's not a bad idea to just label that, right? So here's your 555, and here's pin 3, and then, sorry, that's not QA, but that's input A or something, whatever it's called. And then, you know, put your pin numbers on here and show those going into, you know, U6, which is a 4511 or whatever that is, and put the pin numbers here, whatever they are, and so on. So for the things that aren't standard logic symbols like AND gates or OR gates, just draw a rectangle for the chip, label it with a part number, put that part number in your component ID block, and then just put the pin numbers down. And you know, if this is going to pin 2 and this is going to pin 13 over here, you don't have to put pin 13 over here and run your wire around. You can just label that pin 13. Okay? This is really meant for somebody to say, here's the picture, how do I build the circuit board, or how do I lay it out in Tinkercad? So make this easy on yourself. You don't have to have your pin numbers in order, right? They just have to accurately reflect what gets connected to what. So lay those out side by side, and then you're going to do something with these. You know, some connection of these are going to go into an AND gate, which is going to be, you know, 4 input AND, whatever that number is, a 21. And put your pin numbers on here, and your output goes into whatever the clear input is, 2, which also goes into 3, and that's clear, or reset. Right, does that make sense?
Yeah, that makes sense.
But list all of these pieces and 7-segment display. Right, same thing, you can just list these A, B, C, D, E, F, G. Because we don't actually talk about pin numbers on that one because it's not a standard, you know, like 14-pin chip.
Okay. Thank you. And
Yeah.
you also asked for a test plan. What is that?
So how are you going to tell if this circuit works or not? So the test plan for this, since there's no switches to flip, is mostly, you know, how long are you going to watch it and what do you expect to see, right? if you watch it and it changes from one thing to another, are you done? Are you going to say this circuit works 100%, I guarantee it? How long do you have to watch it for? What do you need to see to say, okay, this passed all my tests? So it's sort of thinking about what's the expected behavior, right? Which is probably going to be, you're going to want to watch it for probably at least 20 seconds and make sure that it counts all the way from 0 to 9, and make sure it goes back from 9 to 0 without any extra delay. So just describe that in a few sentences, and then you know, actually run that test, watch your circuit, and make sure it does what it's supposed to do. And the test plan is going to be more important in Lab 6, because Lab 6 we're going to have a very complex circuit. It's going to be the full three-way intersection, including yellow lights. And so here's how to think of this, right? The wiring diagram is something that you come up with and you can hand to somebody and say, please build this for me. And they'll take parts and they'll take wires and they'll put it together for you and hand you back a circuit and say, here's your circuit. Okay? The test plan is something you can hand your circuit and test plan to somebody else and say, please test this for me. And they don't have to know about sum of products or 555s or anything else. They just follow your test plan. So the test plan says, you know, flip these two switches to off and this switch on. And you should see this LED light up and these LEDs turn off. And so they can flip the switches, they can look at the LEDs, and they can say, yeah, that worked, and they'll check it off. And then step 2 of the test plan says, now flip this switch to the off position, and these two LEDs should turn on, and the third one should stay off. And they'll flip the switches and look at the LEDs and say, yep, that still works. And if your circuit is correct, you know, you'll end up with a whole bunch of check marks. If it's not, somewhere there'll be an X. Test 5, it didn't pass, right? And maybe test 7 didn't pass. And then they would hand this back to you and say, okay, well, you passed 5 of your 7 tests. And so you're not ready to go to market yet. So the test plan is a standalone thing. Somebody could just take your physical circuit or your Tinkercad circuit and your written test plan and tell you yes or no, your circuit works or doesn't work. So for Lab 5, it's really how long should you look at the circuit and what should you see?
Okay, thank you.
Welcome. All right, so any other questions? All right, I'm going to save this because this is a good circuit. All right, so let's take a 5-minute break. Let's come back at about 12:50, and we'll start talking about sequential circuit synthesis and how we actually design a circuit to implement a state diagram. So we'll meet back in about 5 minutes.